Okay, so last class I realized that we didn't actually define what confounding variables were. So I want to start this class off and make sure that we hit all of the 4 variable types that I care about. So the first is the independent variable. And the independent variable, this is the variable that we believe might be the cause of some effect. It's not necessarily the variable that causes an effect, because we're not going to know that. Well, we'll never know that. But we're not going to have evidence that it may be or is likely to be until after we run the experiment. Right? So independent variable is the variable that we believe causes some effect in the dependent variable. So the dependent variable, the idea is that it depends on the independent variable. Now, this usage of the word "it depends" leads some people to interpret the independent variable as it's the variable that just stands on its own. It doesn't depend on anything. And that is hooey. What does the independent variable depend on? So the independent variable depends on itself, right? Because the effect of the independent, that's self-dependent. I don't know. We could philosophically get at that, but there's a more clear answer. So what's Deanna's, Dr. Timmerman's definition of the independent variable? Because the answer lies within it. Dr. Timmerman says that the independent variable is a variable that the researcher manipulates. So who controls the independent variable? The researcher, right. The independent variable depends on the researcher, right? And the research goals and things like that. So it's not that the independent variable doesn't depend on anything. But if we're interested in learning about causal relationships, the independent is thought to be the cause, the dependent is thought to be the effect. So extraneous variables. What are extraneous variables? An extraneous variable is any other variable besides the independent variable or variables, because you might be interested in more than one, that could have an effect on the dependent variable. I say could because until you run an experiment and look at that, you're not sure if they have an effect or not, right? So any variable that could potentially have an effect on the dependent variable is an extraneous variable. So if we're talking about socioeconomic status and how well someone scores on an exam, right, the independent variable would be socioeconomic status, dependent variable is score on an exam. Extraneous variables are things like we talked about last class, whether you got a good night's sleep, did you eat breakfast, what type of breakfast did you eat, did you study, did you pay attention, did you get lucky, did you have the answers, right? All of those other things, those are extraneous variables. Now, a confounding variable is a special type of extraneous variable. So this means that a confounding variable is an extraneous variable. Now this might lead to some confusion on a quiz or exam, because I'll ask you what type of variable something is, and let's say the answer is confounding, and someone circles extraneous, and they're like, but it's an extraneous variable. You said that in class. And I'll say, yes, but that's not the best answer, because there's something else besides just potentially influencing the dependent variable that makes something confounded. Remember last class I talked about when you had something confounded, you basically had this confusion. You weren't sure why things were the way that they were. So, is it the case that people can really tell the difference between one paperclip? Or is it the case that people's left hands are weaker? We can't tell. Why is this the case? Well, every time that the paperclip, or that we had fewer paperclips, we had someone lifting that with their left hand. This means that there's not a correlation because there's no variation. But if you think about it, those two things are tied together perfectly. So a confounding variable is an extraneous variable that is correlated with the independent variable. If there's an extraneous variable that is correlated with the independent variable, you have a confound. So this brings up some problems in drawing claims about causation when you talk about things that you can't manipulate. Things like sex. So women now are seeming to do better on math scores. Why is that? Is it that women are better at math? Is it that women are being pushed harder in math now? Is it that, what's the explanation? And even if I wanted to say that there's something special about having a bit more estrogen in your system, that's confounded with a ton of other things. It's confounded with how society treats males and females differently. It's confounded, and if you think about the way that they're treated, we can talk about the way people interact with you, the clothes that people buy for you, the toys that they give to you, the opportunities they offer you to play. All of these things are correlated with sex. Why are black people getting shot so often by the police? Is there something special about being black? What other things go with being black? What things are correlated with being black in modern American society? Socioeconomic status. Black people have lower socioeconomic status. What do we know about individuals who have lower socioeconomic status?
Commit more crimes.
Why? So they commit more crimes.
Lack of opportunity.
They don't have other opportunities that other people have, right? Well, shoot, I can't get the job, but I've got to put food in my kid's mouth. What do? I'll do something like this, right? So to the extent that race is confounded with socioeconomic status, confounded with stereotypes that lead police and others to have these automatic biases to perceive individuals differently. One of the students that I went to graduate school with, his name is Keith Payne, and he did this guns tool study, where he would briefly show someone a picture of either a black individual or a white individual, and then he'd briefly show someone a picture of either a gun or a tool. So you've got like a hammer, a knife, I'm sorry, not a gun or a tool, but like a weapon or a tool. And all the people have to decide is whether or not they saw a gun or a tool. And what happened? Well, if they saw a black face before that object, they were much more likely to say that it was a gun. So think about that. If the cop is out there, and they have this automatic bias, and someone is pulling out who knows what it is, that cop is more likely to judge that, to perceive that as being a weapon. And if that's a weapon, that's more of a threat, right? So is it their skin color? Is it the stereotypes? Is it the socioeconomic status? Maybe it's the combination of all these things, right? You can't tell. It's confounded because those things are correlated together. This is one reason why Dr. Timmerman and so many other people say that correlation does not equal causation. It's absolutely necessary. If you don't have a correlation, you can't have causation. But a correlation by itself, without those other things, right? Temporal precedence, causal mechanism, ruling out potential confounds, you can't be sure. And experiments are wonderful because they allow us to rule out potential confounds. Now, today we're not going to talk heavily about experiments. Instead, we're going to talk about coins and probability. Yay! And I have some money to offer you guys. We'll see if any of you guys can earn this. Wow. If more than 2 people earn it, maybe we can divide it.
No.
So I have a coin. Can you tell me how many different faces that coin has? Look at it. I mean, I might have stamped it at home to make 2. It's 2. Okay, so there's a heads and a tails. Or heads and building. Tails. So if the coin is fair, what's the probability that it will come up heads?
50-50.
50-50. 50%. 0.5. Right? So, if I flip the coin, whoop, it came up heads that time. I can flip the coin again. I didn't see what it was. But there are 2 possibilities, right? I could flip the coin one time, and I could either come up with the heads, or I could come up with the tails. If both of those types of events are equally likely, then that means that we should see both types equally often. So there should be a 50% chance that we'll get a heads, or a 50% chance that we'll get a tails. When we talk about probabilities, we often don't use the percentages, and instead we say 0.5. Right? A percent is basically 50 over percent, cent, 100. Century, 100 years. 50%, 50 out of 100. So that's 0.5. And same thing with this. 0.5. So, it's pretty obvious that we've got a 50-50 chance to come up with either a head or a tails in one flip. Let me ask you a question. Which would be more likely to observe? I'm going to flip a coin 5 times. Which of those patterns would you be more likely to observe?
The bottom one.
Bottom one? How many of you guys vote for the bottom one? Is that a hand? Okay. 4. So we got 4 people for this one. How many people for the top? 1, 2, 3, 4, 5. Are there other possibilities?
So many.
They're equal. No, not other, so it's more possibilities of that. But other possibilities besides this one or that one, and you said they're equal. So how many think that both of these things are equally likely to occur? Oh, thank goodness. I think this doesn't add up, does it? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There we go. 1, 2, 3, 4, 5. So we had at least 4 people voting twice. Anyway, the majority has it. They are equally likely. So why would people, and I'm actually surprised that it turned out that more people picked this one, because oftentimes when I ask this question, a lot more people will indicate this one. Why do you think more people would pick the second one?
Because it's more random.
It appears like it's more random, right? What does that mean, it appears more random?
It's not really necessarily.
It's not necessarily random, but it has the appearance of being random. If you think about when I talked about p-values earlier, and we're really talking about p-values right now, I said the probability that some result that you observe is due to chance, right? That due to chance, it's basically just due to random stuff. So this looks fairly random. There are some heads and there are some tails, and they sort of look mixed together in a random way. This doesn't look very random. All the ducks are lined up in a row. It's perfect, right? But really, the probability is exactly the same. So who knows how to calculate the probabilities for these things?
Couldn't you, this is off, but couldn't
Yeah.
you measure like the bottom is more likely to happen than the top though? Isn't it more probable that the bottom will happen?
No.
More than it's not?
No.
Okay.
It is more likely. It depends on what you mean by saying the bottom. So if you mean this exact particular sequence of events,
Yeah.
no. They are both equally likely.
Okay.
It is much more likely that you'll get 3 tails out of a flip of 5 coins than all 5 heads. That's way more likely.
Okay.
That's a different question.
Okay.
So how do you figure out the probability of either one of those things? Maybe we can start. Yeah.
Isn't it by each preceding or each one after the first and multiply it by like 0.5? So the first, so getting the second from heads would be like 0.25,
Okay, so the probability of getting the heads is 0.5,
then 0.25,
0.25.
then 0.125, then so on and so forth.
I think something like that. You can, if you've got a calculator. I'm not like calculating these in my mind. They're just familiar patterns. No. After you do this for a while, you get it. In fact, that could be totally wrong. We're very close. And in fact, if you view it in the right way, he's exactly right. So coin flips, they're supposed to be independent of one another. What does that mean, independent in this sense? So I flip the coin once, it's heads. I'm going to flip the coin the second time. It's supposed to be independent, which means it could be either heads or tails. It's true. There's a little bit more to it. Just flesh out that answer a little more. Sorry, one thing. In the discussions, so I graded discussions yesterday, and the online course is kicking all y'all butts in the discussions. So saying something like, oh, math is hard, yes, that is a contribution to the discussion, and I appreciate that. You may have gotten a couple points for it, but try to flesh things out. What about the math is hard? Did you not understand the n-1 correction? Then you can post that. You know, why do we use n-1 in the denominator over instead of n? I understand that this is going to increase the value of our estimate, but why do we do that? Right? Then you've given me and your peers the opportunity to jump in as opposed to, sorry. Also, the math is hard stuff, like tons of repetitions like that can kind of make things like a downer, like, yeah, math is hard, and you know, it's okay, you might feel that way. But if we're positive about it, like, not math is hard, but math is a challenge. It's an obstacle to overcome. Yeah. Better way of looking at it. Right. Okay, so, it's disgusting?
New word.
So what did you say a minute ago, and I asked you to flesh it out a little more? So, it will come up either heads or tails. What's the probability? If so, I flipped it, and it was heads the first time. What's the probability it will come up heads the second time? 50%. This means that the probability of the second event, or the third event, or the fourth or fifth or sixth, it doesn't depend on any of the earlier things. So I'm just as likely to observe a heads in my 100th trial as I am in the first, or the second, or the 28th, right? There's something that gamblers do. They've lost a whole bunch. And what do? It's called the gambler's fallacy.
They'll get it all back and then some next time.
They'll get it all back and then some next time. Right? Oh, I just lost 5 hands in a row. I'm due. I am due. The probability is going to change. Or maybe not, because the probability actually does change in blackjack. But like with the legitimate slot machine, the probability is the same on every single time. So you've pulled it 1,000,000 times, that doesn't mean you're more likely to get it that 1,000,000th first time. So, the probability of getting our first head is 0.5. Notice how there are 2 possibilities, and if we look at 1, the probability here is just 1 out of 2. So if we wanted to get or calculate the probabilities for more than a single event. Let's say we're going to do 2 flips. We can get a heads and a heads, or a heads and a tails, and a tails and a heads, or a heads and, tails and a tails, right? So, we have 4 events. Each one of these events could happen once. So each of these is going to have a 0.25, or 1/4 probability. Does that make sense? Just 1/4. Simple. Now notice here, there are 2 events that have 1 tail. Just like there are 3 events here that have 3 tails. So even though this is just as probable as this, which is just as probable as this, which is just as probable as this, if we consider not getting a head and then a tail, but we just say the probability of getting 1 head, that's much bigger, because we're going to sum up the instances in which we have only 1 head. But he mentioned multiplying probabilities earlier, right? Notice that the second thing he said was 0.25. So there's a 0.5% chance that we're going to get a heads, and a 0.5% chance that we're going to get a heads. We can multiply these things together, and it will equal 0.25. So we can solve this a number of ways. We can do it by, calculating out all of the possibilities, or we can do it by, just multiplying things. So if we have 3 events, 3, we can have head, 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 tail, head, tail, head, tail, head, head, tail, head, tail. Tail, tail, head, tail, tail, tail. Did I get all of them?
Missed one.
Missed one. 12 up?
Head, tail, tail.
Head, tail, tail. Thank you. Head, tail, tail. Beautiful. All right, so what's the probability that we'll get this? 1/8. Which is 1, 2, 3, 4, 5, 6, 7, 8. So each of these potential things is equally probable, right? So it'll be 1/8. So 1/8 is, I believe it is, what, 0.125? And that is just equal to 0.5 times 0.5 times 0.5. So simple. We can calculate this stuff fairly easily. Now, what I'm doing up here is I'm actually working through a particular type of distribution known as a binomial distribution. So a distribution, writing this down, I'm not even sure. Okay, whatever, write it. Okay, so it follows a binomial distributions, and different distributions are defined by different parameters. So the binomial distribution is defined by the probability of getting a successful event. We can define the success as getting the heads or as getting the tail, right? In this particular event, the probability of success is 50%, right? So we've got a 50% chance of success. What else does the binomial distribution depend on? Probability of success, and I've run through 3 examples. In what way have the examples differed? The number of events, the number of observations that I take. So the binomial distribution depends on 2 parameters. 1, the probability of success, and 2, how many observations you take, right? So if I were to flip a coin 100 times, and that coin were fair, how many times would I expect to see heads? 50, right? 50% of the time I would expect. Now, if the coin really is fair, and we did this thing over and over again 100 times, what would happen is all of the means of all those means would be the true mean, 50. However, for any one flip of 100 coins, I might not get 50. What might I get? 49, 48, 100. Highly improbable, but possible, right? So if you think about it, knowing the parameters of some distribution allows us to make a claim about what we would expect to see. And then the data that we collect, our observations, give us something, right? So we have a difference potentially in what we expect to see and what we actually observed. But we know something else. Not only do we know what we observed and know what we expect to see, if we know the parameters or can estimate the parameters, we can figure out how likely or how probable it is that we would observe certain patterns. That's exactly what we were doing up here. What's the probability that you would observe this? Well, it was 0.125. Yes. Right? We calculated that out. So, the money-making opportunity. Let's do this now. I'm going to flip the coin, and we're going to see if any of you guys are psychic. So, what I'd like you to do is everyone get up and get in the middle of the class, and actually, if not get in the middle, if you think it's going to be a tails, go over there. If you think it's going to be a heads, go over there.
I'm closer over here.
I was going to tell him first, but I think I always get it wrong.
Oh, good.
Okay, are we ready? I'm going to try to catch it and then put it on my hand like this. If I drop it, I reflip. Okay, I'm setting the rules up in advance. Here we go. It is tails. So you guys can all have a seat. Now, same thing. So you guys are all still playing. If you want to stick with tails, stay over there. If you want to move over to heads, go over there. So the first one was tails.
Goodbye.
Really happened. It was a long
I
one.
got a lot of homework today. This is my exercise.
All right, you guys ready? Flip it again.
I know, there was the heads.
Tails.
Dang it.
Holy cow! Are they all psychic? Lazy? Would it be reasonable for me to say that they're psychic at this point?
No.
No.
Okay. Want to teach?
Sorry.
Tails! Really? Uh-huh.
Let's see the other side.
Derek, you got coffee. I hope to lose.
Yep.
Sorry, honey. All right.
Give me the $5.
Heads.
Yeah, this whole time I got that.
And it's down to our final six.
Holy cow.
Way to do it. We'll split it.
I mean, they can't both be psychics because they're splitting on this one.
They're conspiring.
Oh! It was tails. It was tails.
Oh, you dropped it though. You got to reflip.
Wait a minute. Weren't you tails?
Yes.
You're good. So you sit down.
Yeah, I'm going.
This is-
I'm getting a little extra exercise here. I make it so she's never gonna actually get it if she wants.
Okay, we'll stop here.
Yeah.
We'll stop here. Go ahead, sit down. But before I give her the money, we have to ask, is this sufficient evidence to conclude that she's psychic, given the rule that psychologists use for making these types of decisions? So, what am I looking for here? Evidence, yes. We're looking for a probability of something. Probability of what?
Oh, she's right.
Probability that she's psychic? No.
How often she's right given the trials.
How often she's right given the trials? Can you give me a little bit more?
So if she's right 5 times out of 5 versus right 1,000 times out of 1,000.
Well, if she was right 1,000 times out of 1,000, I would argue that that's much, much more convincing evidence.
Yeah.
The question is this enough evidence for me to give her the $5 based on the way psychologists operate?
You're not going to give her $5?
We will see.
No, because it's going to be based on chance.
It could still be based on chance. That's what I want to see. I want to look and see what the probability is that she could get that just based on chance. Right? In fact, that's not the whole part of how psychology operates. It's not just the probability that she could get this based on chance. It's the probability that she could get this or anything that is as or more extreme than that due to chance. Because if you think about it, if really I had everyone up and doing this, it's possible that someone is sort of like anti-psychic. They're psychic, but they're wrong every single time. In which case, if you know this, you just bet against them and you got it made. You don't even have to be the psychic. You just have to know that they're anti-psychic, and then you can do the opposite.
But then
Right?
they're psychic.
No, you're not psychic. They're really the psychic.
Yeah,
But they're just confused psychics.
Flip it one more time. Let's see if she gets that.
We will...
She was going that way.
Maybe we have enough evidence at this point. So how do we figure out if we have enough evidence? What's the probability that she would get one right out of one flip? 50%? We can draw something that's called an outcomes matrix. And we have what she's predicting, heads, tails, and also what's observed. Heads, tails, right? So it could be heads and she said heads, it could be tails and she said tails, it could be heads and she got it wrong, it could be tails and she got it wrong, right? There are 4 potential combinations because there are 2 things that she can say, and there are also 2 ways that the coin can flip. But if you notice, the important thing is that she's right 50% of those times. So, this means that the probability of her getting one right, I'm going to say P represents probability, one right, equals 0.5. Probability of getting 2 right in a row, what's that? 0.25. If she's not psychic, right? If she's psychic, we really don't know. Is she perfectly psychic? Is she just a little bit psychic? Or is she a lot psychic? Unless we have some specific value that we want to go with. Like, we can't really calculate those out. However, if we know the probability just due to chance alone, we can calculate this stuff. So, probability that she'll get 2 in a row is the probability that she'll get the first one right, times the probability that she'll get the second one right, and that should equal 0.25. Right? What's the probability that she'll get 3 right? Does someone have a calculator? Because I want to make sure that we get the numbers right this time. So, 0.5, and now this is going to be to the 3rd power, right? We're multiplying 0.5 times itself. And 0.125, is that right? Oh, good, we got the calculator. So multiply it again. What's the probability that she'll get 4 right in a row? 0.0625. But she didn't get 4 right in a row. She got 5 right in a row. P, getting a 5 in a row, equals what? 0.5 to the 5th.
0.03125.
0.03125. Good. My memory worked great, even though I couldn't do the calculation in my head. So that's perfect.
Better than chance.
Better than chance.
Wasn't this P's something?
P.
Less than 0.5.
P, the rule. P is less than 0.05. So the probability that we would expect someone to get 5 right in a row is less than 0.05.
Yes. Are you going to go with both?
No. I'm going to stick with the traditional value. Because I'm a traditional kind of guy. Although that's actually a logical fallacy. Like, oh, history's done it this way, so we should keep doing it. But whatever. Let's pretend I'm a traditional guy. All right. So traditional guy, P, the probability of getting that set is less than 0.05. However, the p-value doesn't represent the probability of observing your results due to chance. It's the probability of observing results as or more extreme than what you observed. So what is just as extreme as getting 5 right in a row? Getting 5 wrong in a row is just as extreme. So the probability, so this is 5 right, probability 5 wrong, same thing, 0.03125. So what's the probability of getting a result as or more extreme? Are there any possibilities that are more extreme than 5 right in a row when you do 5 flips? What's more extreme than getting 5 right in a row out of 5 flips?
6 or 7 or any more than
But
5.
you can't. Can you get 6 right in a row out of 5 flips?
Predict the next one.
No, you can't. So out of 5 flips, you can't get any more extreme. If you do 6 flips, 6 in a row is more extreme than 5 in a row, but we haven't done that yet. So, how do we get the probability of results as or more extreme than what she got, right? We have the probability of her result. We have the probability of results as extreme. So the probability of results, I'm just going to say P, because this is the p-value we are talking about right now, equals 0.06225. How did I get that? I just added those probabilities together. If you think about the probabilities, all of the probabilities have to add up to 1, right? We have 2 events, probability of this plus the probability of that, 1. We have 4 events, probability of this times the probability of that times probability of this times the probability of, or plus the probability of that, plus the probability of that, plus the probability of that, 1. right? It's probabilities, they can't be more than 1. It's just like effort. You can't put in more than 100%. 100%'s it. Can't have a probability higher than 1 or 100%. Yeah, I've got a 200% chance. No, just 1. Adds up to 100. So all we need to do is just add up the probabilities that contribute to the thing that we're amazed of by its extremity. So is 0.0625 less than or equal to 0.05? No.
No.
My money is safe for now. What do I need to do?
Yeah. One more time.
One more time? I'm not going to make you walk, unless you want to. Maybe that's part of your psychic thing. You've got to walk. Do you want to walk, or you just want to call?
It's like Rocky.
Okay, so what is it going to be? She said it's going to be tails.
He says.
Oh!
Should have stuck with the head.
I didn't even see that.
Yes! She got it wrong. You You know, I give out a lot of money over the years. Why would I give out money a lot over the years? I don't give out a lot of money each year, but
Probability isn't in your favor.
the odds, well, it depends. On what?
How often do you do this?
What?
How often you do the money experiment?
It depends on how often I do the money experiment, yes.
How much you offer?
It depends on how much I offer. I've offered up to, I think, almost $50.
Did they win it?
No, they didn't.
Oh.
Do you like up the money value each time?
No, I don't.
Actually, are you like?
No, this was just in a class where they really wouldn't participate, and I was like, I gotta get them doing something. So I bribed them like crazy.
Oh, so we're cheap.
So, what does it depend on?
If you go until somebody like, gets it wrong, or if you say I'm doing it.
If I go until somebody gets it wrong, no, I mean, I stopped when the class told me to stop, and then I looked at the data and I said, okay, well, you know, we need to collect more data, right?
But if you had like, if you were saying I'm going to do it out of 10 trials.
Okay, which I should do beforehand, because if I don't have a set stopping point, then you could like accuse me of p-hack. In this case, trying to hack it until I observe something that keeps my money in my pocket. Yes. So I should have said out of 10. Should I do out of 10?
No, that's a lot.
Okay.
Well, up to 6 inches or more.
I can keep my money. Thank you. Good try.
Working plan.
You can have a nickel. The probability that it would go into her eye is so low that I felt confident that if I tossed it to her like that, I would not get sued. One of these days I'm going to be wrong. And what it depends on, imagine I had a class with like 100 people. What would the probability that I would like give away the money? Just say higher, yeah, higher, right? Why?
More trials.
More trials. So think about it. All someone has to do is get 6 right in a row, and that's convincing enough to me, right? So imagine you've got 100 people, and let's say it's really random how they're deciding who goes over to which side. So the first flip, how many people do I get rid of? How many would I expect? Yeah, I would expect to get rid of 50, right? So I've gotten rid of 50 after the first. So now, how many do I get rid of after the second?
50%.
I get rid of half of that, so I'm left with 25. Then I do it again, how many am I left with? Half. So let's say 12 instead of 12.5, because we're not going to have half a person. So we're left with 12. I do it again. How many am I left with? 6. I do it again, how many am I left with? 3. I do it again.
1.5.
If they split that last time, someone, or maybe 2 people, are going to get it. What does this mean? Does it mean that the person got it is psychic? Not necessarily. It could mean that. But what else could it mean?
They were that part of the percent that did get it.
They were lucky. They happened to be one of those people that you would expect just due to chance that should get it every once in a while, right? It's not going to happen often. I mean, what are the odds of winning a lottery? They're really low. But yet people win lotteries all the time, right? Because they keep running them until someone gets it, and the bigger the jackpot gets, the more people buy the numbers until all the numbers are taken, and someone has got to win, even though the probability that you will be the winner is almost nothing, right? So, this means a couple things. When I set up the p is less than 0.05, there are a couple different outcomes, and we can draw an outcomes matrix. So let's say this is the truth with a capital T. And we can say that there is an effect of something. There's an effect of socioeconomic status on aggression, maybe. Or maybe there's no effect. And we have our conclusions. Conclusions. Which may or may not be related to the truth. So we might say that there's an effect. We might say that there's no effect. And so if there is an effect, and we say there is an effect, does anyone know what we call this type of an outcome? This is a hit. It's like going up to bat, and the ball is here. And with the bat, you can say where the ball is. And if you say the ball is where it is, what happens? You get hit. What if there really is no effect, and you say that there's no effect?
Yes.
How did you miss it if there's not really anything there? Did you miss the ball if it didn't go over the plate?
Yes.
It's not a miss. What would a miss be?
You say there's an effect, but there's no effect.
You say that there's an effect, but there was no effect. Ooh, someone said type 1 error. Type 1 error. Wait, so if you miss something, does that mean you said it's there? Like, and it's not? So there's a fire in the school, and I'm like, holy crap, there's a fire. Or let's say there's no fire, but I'm like, holy crap, there's a fire. Ah! Did I miss the fire? Oh, I invented it. So what's a miss? Think of miss. What happens when you miss?
There's something there and you don't say it.
There's something there and you don't say it. So a miss is when there is an effect, but you missed it. You didn't say that there was. So this is the miss. So there are two other types of things. There are hits, misses, there are correct rejections, and there are false alarms. So what is the false alarm like? There's when there's really no effect, but you say there's an effect, that's a false alarm. Which means that this is a correct rejection. So when we set up our tests, by the mere virtue of using, it's gone, p is less than 0.05, less than or equal to 0.05, what does this guarantee some of the time? What would happen if she got that last flip right? She would have got the money, which is like me saying what? It's like me saying there's an effect. There's, you know, she's psychic. Is she really?
Yes.
He's shaking his head no, he's shaking his head yes. Someone who really took that first class to heart might say we don't know. There's still a possibility. That's true. But what it means is that if there's never, ever, ever an effect of anything in the world, just due to chance, we're going to be saying that we found something 5% of the time. 1 out of 20. That means if there are no effects in the world, then at least 1 out of, wait, if there are no effects, then all the journal articles are wrong. Or at least most of them. But this means that a lot of the journals, or the journal articles that could have been published, might have just been chance effects, right? Meaning that what is really important? If we want to eliminate the possibility. Or we're not going to eliminate it completely, but we want to reduce the possibility that we got it wrong. What can we do? We could do it again. Do a replication, right? Run the experiment again. So, someone said type 1 error. Okay, so we have some things that are correct. These are correct. These are errors. Does anyone know what this value is referred to as? If you've taken stats, hopefully you'll know. I'll give you a forced choice. Is it alpha or beta?
Alpha.
Alpha, yes. And alpha, who decides what alpha will be for any test?
Person running the test, right?
Person running the test, that's exactly right. So the person running the test decides what they want this to be, alpha. So alpha is the probability at which we're going to say, look, it's unlikely that it's just due to chance. And alpha is sort of arbitrary. Why pick 0.05? That's 1 out of 20. We could have picked 0.01, which would be 1 out of 100. It's sort of arbitrary. If you make alpha higher, you're more likely to say, oh, we found something, we found something. If the alpha level was at 0.1, or we're willing to be wrong and say that there's an effect when there isn't 1/10 of the time, she would have taken my money. But fortunately, as a traditional guy, I went with 0.05. So alpha is really up to the researcher. So if alpha is 0.05, then we are making a mistake. Alpha represents the probability that's just due to chance, right? That means the probability that there is no effect. So what type of error is related to no effect? It's the saying that there's an effect when there's no effect. That's a false alarm. So this is our type 1, or our alpha error. So what comes after alpha? Beta. Beta isn't the probability that's related to chance alone. It's the probability that you will identify the effect when it's there. So this means that you have an effect. And if you don't identify it, that means you made an error. So this is the type 2, or the beta error. If you think of Michael Jackson, back when he was young and sweet, A, B, C, it's easy as 1, 2, right? A, B, C, 1, 2, 3, alpha, beta, 1, 2. Alpha, beta, 1, 2, you got it. So this means that scientists are going to be wrong some of the time. Sometimes we will say that there are effects when there aren't. Other times we will say that there is no effect when really there is. And we manage alpha and beta in order to decrease the possibility that we are wrong more often than not. I'll see you guys on Wednesday.